wide open. All right, maybe no, it's okay. It's 1:05, so I'm very happy to yield the podium to Anton, who will tell us about counting over finite fields.
Okay, thank you. So, as I read on the website that it is an informal seminar,
that is correct.
So my plan is to spend the first half of the time to show you some formulas, hoping that you will get used to my notations, and then afterwards show some new formulas. So, okay. So can someone stay on video so that I see that some facial reaction? Oh, great. Thank you. No. Okay. So, okay, let's see. So I really like this thing of counting over finite fields because very often you get very easy way to get formulas without extra technicalities, but for some reason it's not so popular, especially among people who work over complex numbers. Let's start with, so first I need some, okay, let's talk a little bit about lambda rings. So when we count some invariants of some geometric objects, we get answers, and these answers are elements of some rings, but usually they are also elements of this ring. Usually these rings are also lambda rings. And so what is a lambda ring? A lambda ring is a ring R with extra operations called Adams operations, such that, so these Adams operations are psi k, where k integer, and they satisfy, they are ring homomorphisms. And second is that they form an action of the monoid of integers with respect to multiplication. So you have this. Okay, and examples of these lambda rings are K theories, K groups, also homologies. Well, so many things that come in from geometry. And the way to think about them is usually you think about the K group of something, and more natural operations are the symmetric powers and exterior powers, and they can be expressed in terms of the Adams operations by a formula that sum sim k of some x.
But it's only over rationals they can be expressed, no?
Yeah, I assume that all my rings contain rationals for simplicity. Of course, you can do more sophisticated things. So this is a formula. Sorry, I sometimes use a different font. And of course, then you have this formula. So the problem is that these natural operations have two very difficult identities. And so on the other hand, Adams operations have very easy identities that I already wrote in the definition. Okay, now once we have a lambda ring, a good thing to do is to extend Adams operations to action of the ring of symmetric functions. So since I used sim for a wrong. Okay, let's denote the symmetric powers by S. So consider sim is a ring of symmetric functions in infinitely many variables. So you have x1, x2, so on, invariant under the action of the infinite permutation group. And of course, this is also just polynomials in the power sum functions. And the way that if, so let f be an element of this ring, and then let, so write it as f of P1, P2, sorry, and so on. And then take X in some lambda ring, then f X is defined by just evaluating this Adams operations on X, okay? So this is called pletistic substitution. Pletistic substitution. And everything is defined in such a way that Hn of X is symmetric power, where Hn is complete homogeneous symmetric function, and En is the exterior power, where this is the elementary. Sorry, this is not clear here. Okay, good. So this is a way to pass between operations and symmetric functions. Now, here are some examples. So sometimes we have some element in the lambda ring which behaves like a line bundle. So we call X, I don't know, line element. I think this is what Kontsevich-Soibleman call it. If all exterior powers vanish, for K is at least 2. Equivalently, it means that psi operations, which are the same as P operations. So let's start using P. Okay. So all Adams operations simply raised to K's power. And in many interesting situations, it's enough to consider a ring generated by line elements, and then we know how all the Adams operations are defined. They are just raising all variables to the K's power. But there are other situations. So, okay, and then one example. So let's compute H. So this is, I don't know, this is my favorite formula. So I hope. Let's compute this where So U and Q are line.
This is going to be the Q binomial formula, right? Is it?
Yeah. So how do you? The point is that you to compute it, you don't really need to do any. I don't know. Yeah, it's pure algebra. Well, it's pure algebra. So how do you compute this? You write, for instance, you try to find some equations or recursions. So one would be this one. So start with q to the n, hn of this. So this, okay. So it's easy to check that if function has degree n, then any line element can be just moved in it. It's homogeneous. So you get this. Okay, now I want to rewrite it in terms of the original. So I get q minus 1, which is 1 plus 1 minus qu 1 minus q. And then there are these formulas that hn of x plus y is the sum of I plus j equals n, hi of x, hj of y, and hn of minus x equals minus 1 to the n en of x. So using this, we quickly get that this is equal hn of 1 minus qu 1 minus q minus hn minus 1 of the same thing. 1 minus qu 1 minus q. Okay, that's one thing I wanted to compute. And then I want to expand hn of 1 minus u over 1 minus q. I want to now play with u. So I want to take 1 minus qu plus q minus 1 u. Right? And then again, q minus 1 over 1 minus q is minus. So again, we are lucky that the sum will have only two terms. Minus u times the same hn minus 1, 1 minus qu over 1 minus q. See? Now I have two identities, this one and this one. Right? I can subtract. So I get hn of times 1 minus q to the n equals, and so it's a second minus the first. So 1 minus u hn minus 1 of 1 minus qu over 1 minus q. And so I see that you get an infinite, sorry, not infinite, you get a product. And the product is like this. You get 1 minus u, 1 minus qu to the do, 1 minus q to the n minus 1 u. And in the denominator, 1 minus q, 1 minus q squared, 1 minus q to the n. Okay. So we obtain this formula. So I think it's very useful to program. At some point, I programmed these platisms and I play with them on the computer. But for some reason, all the standard software doesn't really have them. Everyone has to program them from scratch. Okay, so you can, for example, compute this thing. You can compute, or you can compute now En 1 minus u. So how would you compute En? Well, you know that it's minus 1 to the n hn of the minus. So it's u minus 1, 1 minus q. And then you want to make it in the same form as before. So you move out u. So you get minus u to the n hn 1 minus u inverse 1 minus q. And now u inverse is again line element. So you can use the formula. So use the formula. And so what does it mean? I have to substitute u inverse and then multiply by minus u. So you get 1 minus u, q minus u, q to the n minus 1 minus u. And the denominator is the same. Okay. So you have this. Now what you can do, you can set things like, what if u equals q to the k? Then you get that hn of 1 minus q to the k, or 1 minus q, is, well, basically the q binomial. And then this is also equal hn of 1 plus q plus q to the k minus 1. Yeah, why do I want to use this thing? Because of the binomial identities. The point is that you can do things like, okay, let me finish with this first. So this is well, so this is, I have a formula for this. I now can also set q equals 1. I get the formula for hn of k. Hn of k becomes n plus k choose k. Oh no, n plus k minus 1 choose k, right? If I get q equal u equals q to the k, plug it in, I get the product up to q to the q plus n k plus n minus 1. So I get this. And now so this holds for all integers, for all positive integers. But by analytic continuation, you have that hn of k equals n plus k minus 1 choose k, where now this is a, maybe, okay, like this. Now this as a polynomial in k, but k is not arbitrary. So this is, you see, I proved this identity under specialization when k was an integer. So this means that I was using, so this new identity works under the assumption that Adam's operation preserve k.
Sorry, Anton, what's h1 of k?
Okay, now we are talking.
Yeah, no, h1 of k, is that k?
h1, by definition, is just the sum of xi's as a symmetric function. And so it's equal to p1.
Yeah.
So h1 of anything by the axiom is just the same thing, x.
Right. So if I plug in 1 into your formula,
Yeah,
I get k choose k, which is 1.
yes.
But that seems
Maybe
not
it's times k.
Wait,
The
wait.
polynomial coefficient times k, right?
You mean I made a mistake?
I think.
No, you like suppose that this k is 1 or something like this.
N equals,
No. Maybe not. Sorry. No. I'm sorry. Not really.
oh, wait, maybe I made a mistake.
Maybe you just want to choose k minus 1 or something.
If I set, I get k plus n minus 1, k plus n minus 1.
I think there's a formula like that, which is correct. I think we can work out what it is.
I just want to make sure I wasn't missing something.
I think let's not make it too informal.
Damn, this is really embarrassing.
It's all good.
Each one of k.
Let's leave it as an exercise to the audience to find the right formula for binomial coefficient.
I'm getting old. I have to say. Okay. Well, so there are these identities, and they really work under the proper assumption. So this is so quotient is the following. So you see, I got two different formulas for Hn, completely different. One is the Q formula, and another is the binomial formula. And of course, they cannot be true like all. It cannot be true, both of them. So when you prove, then when you prove the formula under some assumptions, then you can only use it under substituting things satisfying those assumptions. So you have to plug in things satisfying these assumptions. So for instance, if you have a line element, so if Q is a line element and you want to plug a number, you're only allowed to put numbers. So if you want to set Q equals a number, then this number must satisfy the number to the K must be equal to a number. Then we require this. And so number must be 0 or 1. So it's a bit
Sorry, I missed that. So line element means Q to the line element
means pk of x equals x to the k.
And since this is supposed to be linear, but this is supposed to be linear over. This is supposed to be linear over numbers, and so you say if a number satisfies it's 0 or 1. Okay.
Sorry. So I am only have. I suppose I have this. I have some identity which involves x, and that x was supposed to be line element. So it means pk of x equals x to the k. Then if I have some other element in some other lambda ring, which also satisfies pk of x equals x to the k, then I can plug it in. Now suppose I want to plug in numbers, elements of Q. On numbers, pk acts identically because pk is supposed to be ring homomorphism. So if x is a number, then x equals x to the k. If x is a number, both a number and a line element, then x must be equal 0 or 1. That's what I'm saying. Okay. But sometimes you have identities where you have, sometimes identities don't have any assumptions. Like on some object X. And then you can plug in anything. So for example, Hn of x plus y equals sum I plus j equals n, Hi of x, Hj of y. Okay, so this is identity which is just universal. You can plug any x in any lambda ring and any y in any lambda ring, and then you're fine. Okay, so I just wanted to fix this issue because this is somehow people still get confused about what does it mean to have an identity and then statistically substitute something in it. For instance, I don't know. Okay, so there is this useful thing called statistic exponential. And this is just, by definition, is the sum of all Hn of x. And example, you can write now, compute now x of one. So let's see something like this, x over 1 minus q. So x line element, you can compute it in two ways. So on one side is by definition, you get x to the n over 1 minus q to the n. Right, I just Hn, I computed from the previous formula for u equals 0. I get just the product of 1 minus q to the n. On the other side, on the other hand, I can compute it like x of x plus qx plus, I don't know, q squared x. And then this is infinite product. So I get already a non-trivial identity. So maybe trivial for some, but that infinite product is expanded in this infinite sum. Okay, now this was about lambda rings. Now let's go to the next point about counting over finite fields. So so if you have a variety over finite field, then you can compute points on it. So in general, x variety over of q, you get a number. X is just a number of points. So if x is given by some equations, so given by equations, then you solve the equations, or it counts some model solution to a modular problem, or then you can extract the number. And so the first example is the Grassmannian. So you take Grassmannian of k-dimensional subspaces in the n-dimensional space. How do you compute that? How to specify a k-dimensional subspace in the n-dimensional space? You choose a basis. So you choose the first vector, for the first vector of the basis, you can choose any non-zero vector. Then you can choose any vector except vectors parallel to the first one, and then so on. And then in the end, you have to, you get this. But then every subspace is counted many times. So as many times as there are bases in the subspace. So you get this. And this is again some kind of Q binomial. So more interesting, you can count.
So in general, so then would be by this kind of argument, if you're not you don't have a variety but rather a stack of some kind, you're counting points not with one but 1 over the order of automorphism.
Yes. But I will specify in graph. So far it was just Grassmannian. Now similar partial Frege variety. For that you choose some partition. So you have some entries, so that sum equals n. And then you want to count partial flags whose steps are given by lambda. So we have, okay, partial flags. And then you just can apply the same formula for the Grassmannian, but iterated. So you get Q multinomial. So it will be, you can do cancellations. So let's start like this, Q square minus 1, Q to the n minus 1. So rising Q powers. And here you will have product over I of things like this. And now here here I will want to demonstrate the power of symmetric functions. So let's assemble all this information into one big symmetric function. So usually we count something for each partition lambda, and that's something. For that something, lambda should give. You always will be counting something which involves partial flags, something with partial flags, and lambda will control the steps of flags. And then we want to write sum. So you get a number. So with this number will be, I don't know, get C lambda is an integer. And then we write C lambda M lambda, where M lambda is a monomial symmetric function. C. And another way to say this thing is that C is equivalently C is a sum of monomials. So some A, x to the A, where we have our alphabet. And then we put here times the number corresponding to the partial flux with steps given by A, CA. Okay. So if we want to do it now for the counting all flags in the vector space, then we get the following. So for all flags in the vector space in fq to the n, we obtain a sum of m lambda, lambda partition of n, and then this formula I want to interpret it as a product over I, h lambda I of 1 over 1 minus q, and then the overall factor 1 minus q. I changed the signs everywhere, so I think nothing changed. Okay, and this is the, so there is some notation. H lambda is the product of H lambda I for a partition lambda, and there is a formula Hn of a product of two things is the sum of partitions m lambda of first thing and H lambda of the second thing. And so therefore this C equals 1 minus q to 1 minus q to the n times h n of x over 1 minus q. Okay, so x is here. If you are confused, I kind of omitted it. Everything is depending on x. C of x. Is that clear? So it turns out there is a much more powerful and much more general theory containing this formula as a special case, and this is a theory of Hall-Littlewood polynomials. So how does it work? Maybe, okay, let's move to the next page. So the simple idea is I want to fix, so let n mu be an nilpotent matrix. And I want to count flags. So let's play the game. Let's count flags preserved by this n. So what is so what is n mu? What is the notation for n mu? So so n mu is I mean, of course, every nilpotent matrix can be made into Jordan form, and this is just Jordan blocks of sizes mu that transpose partition, so that we have mu1 is a dimension of the kernel, mu2 is the dimension of the kernel's square modulo kernel of n mu square modulo kernel of mu, and so on. So this is my convention for passing between nilpotent matrices up to conjugation and partitions. Okay, so counting flags preserved by mu by this nilpotent matrix. Of course, I will again be counting partial flags like before, and I will get symmetric function. And if you want to connect it to some more sophisticated mathematics, then this is a Springer fiber. I will counting how many points are in the Springer fiber. And so how does it work? So there is a, so let me sketch the main ideas. There is a category where objects are like representations of one loop quiver, which are nilpotent. And this is a abelian category of dimension 1 with trivial Euler form. And you can consider the whole algebra. And this goes as follows. So the algebra is a formal linear combinations of objects up to conjugation. Formal linear combinations. A mu x mu. No, this is a number, and this is an object. Consider it up to equivalence, up to isomorphism. So what is the operation of this whole algebra? There is so the structure. There is a coproduct. And this is very naive thing. When you have something, you should produce two things. And this is given by taking a sum and a quotient. So sum overall z in x, and then a class of z times class of x minus z. So it's commutative in this case. So we don't have to worry about which comes first and which comes next. Then you have scalar product, a pairing, and this is defined by, if I have two things, then the scalar product is just a number of isomorphisms. X and Y. And then I can dualize the coproduct. Dualize the coproduct using the scalar product. So let's number them 1, 2, 3. Dualize the coproduct 1 using 2 and get a product. And of course, in general, you could take any coproduct and dualize it and get something, which is again associative. But the mystery here is that by in this kind of situations, there is a theorem of Green. Theorem tells you that you get a Hopf algebra. Now, on the other hand, symmetric functions, so it's yeah, infinitely many variables also form a Hopf algebra. Okay, maybe I should. I mean bi-algebra. It turns out to be Hopf algebra later. It's important that it's bi-algebra. So symmetric functions in infinitely many variables form also a Hopf algebra by. So you see, if you have a function in finitely many variables, you cannot make a Hopf algebra because from n variables you cannot make again n and n. But if you have infinitely many variables, then there is no problem in doing that. So you can send function x1 of these variables to f of x1, y1, x2, y2, so on. And you get two copies of infinitely many variables. And that's how you get a Hopf algebra. Okay, and you can see that it's, again, it is a commutative, co-commutative Hopf algebra. There is a scalar product, and you can try to identify the two. So you want to identify, on one side, you have the whole algebra of this category of nilpotent representations of one loop quiver and symmetric functions. And how you do that? You write, so there is a neat way to do it. As follows, you write, take some element, x, apply iterated coproduct, and you get n things. And then you how do you say it? So you replace x1, xn plus 1 by little x1 to the dimension of x1, x plus 1 to the dimension of this object. Okay. So so you make all variables keep track of the dimension, and then it is clear that, and this is preserves the coproduct, and then it preserves, you check that it preserves the product, because for that it basically follows from the fact that dimension of an extension is the sum of the dimensions, and then you want to compute the image of the scalar product. Of the scalar product, and we obtain not quite the usual scalar product. So the modified, so the Q modified scalar product, which is as defined as follows. So there is a the usual product is given by, there are many different equivalent ways, but one way is to say that the complete homogeneous functions are dual basis to the monomials. or you can say that the power sums are orthogonal with the coefficient, or the Schur functions are orthonormal, and the modified one is given by so if you have x, two functions f and g, and this stands for the modified, then you have to do this substitution, q minus 1x, and take scalar product with g.
This Z here for the pairing with the P's, that's this arm and leg business.
This Z is the size of the centralizer of the corresponding permutations. You can look it up.
Okay.
So this is a modified.
Yeah, but I mean that's just like a L2 inner product of conjugacy classes on symmetric group, and so it's just like has to do with the size of the conjugacy class. So it's and the size of the conjugacy. Yeah, I mean I'm just answering to Ono's question. Yeah.
Yeah.
It has to.
Product of lambda.
The P functions go to conjugacy classes on symmetric group, and so that's just different conjugacy classes have different size, and so it's.
Okay, so there is this modified one, and the proof basically.
And that's just like basically the conjugacy classes in general linear group, right? More or less. Yeah.
What? Which one?
Over. If you think of the symmetric group as this is like it's like a general linear group of a field over one element.
Right, I guess it should be the same thing. Yeah. So proof is like everything is almost automatic. Thing is almost automatic, except there is one thing that you need to really compute, and here is what you have to compute. So you see this function that takes the dimension of a representation. What is it? We consider I of u sum of all objects and then put the class of the object divided by the number of the automorphisms and times u to the dimension. So basically everything what when we constructed our map to symmetric functions using this single series, which is a group-like element in that Hopf algebra. And basically you can convince yourself that knowing where this group-like element goes completely fixes the homomorphism of Hopf algebras. So this group-like, where it goes specifies the map, and then what you want to do, you want to compute the scalar product of IU. No, you want to compute the image of IU is now the sum of. Right, you have to compute the image of this, and did I have notation for this map? Was there isomorphism between? So let's image of IU is Now we have to go over some overall. So we have to go overall objects, overall partitions, and then we have to go over one of the automorphism group. So this is the centralizer of that nilpotent matrix. And then we have to count flags, which are preserved by this matrix. And now we just use the following trick. So first we write it as a sum over, so 1 over the centralizer is the same as sum over all nilpotent matrices. We'll take 1 over the size of the group if lambda is fixed, and then we have go over sum over all nilpotent matrix M, and then we put here a number of flags preserved by M. And we didn't change the order of summation. We first sum over flags and then sum over nilpotent matrices. And it's very easy to count how many nilpotent matrices preserve given flag, because they must be just upper triangular. And so you get some nice formula. And actually you get Hn u to the n, Hn of x over q minus 1, something like this. And this number here gives you that the modified scalar product has q minus 1 in it. We are, I don't know, we're reproducing kernels. So, I don't know. So exercise. So this is a real exercise. Like if you do it, then you will feel that you you understand everything in this first part. Okay. So right, and then the point is that where do the actual objects go? We did all this abstract algebra, but we didn't even understand this basic thing. No, and the answer is to the modified Hall-Littlewood polynomials. And what is this? So if you studied usual Hall-Littlewood polynomials, so recall the usual Hall-Littlewoods are like p lambda q, and they were such that if you expand Schur's in terms of them, get some q Kostkas q Kostka numbers, and the idea is that instead let's expand the other way around. Let's expand instead of p. Well, so you can consider h lambda transposed. Now these are polynomials. Also, this is a dual basis to p lambda. And then we will have formula like this.
means dual with respect to the ordinary scalar product.
With respect to ordinary. Ordinary. And we get the formula like this. And right, and this is, so it turns out that these are the ones that control the elements of, these are the images of the Hall-Littlewood, of the actual nilpotent matrices. So example, for me, I just have to keep in mind these two examples to remember which polynomials do we get. So first example is when lambda is n. So this means that n lambda is just a zero operator. So we are counting flags preserved by zero operator. And so we get this formula that we had in the beginning. Hn x over q minus 1. 1 minus q, sorry. And lambda is a regular. So there exists exactly one flag of each type, which it preserves. So we get Hn, sum of all monomials with coefficient 1. Okay, so okay, so now the main point of that. So I don't know how seriously you were when you wrote that the talk is 90 minutes. You're muted.
It is 90 minutes, yeah. So it's and in fact, so officially you have 28 minutes. No, even more.
Okay, no, I don't want to.
28 minutes more, yeah.
So you see, we had this nice picture where we had we were studying nilpotent matrices and flags, and we got symmetric functions. And the problem I really liked is how to get Macdonald. So what are these Macdonald polynomials? They are they satisfy. So I put this tilde to also distinguish the Macdonalds from Hall-Littlewood, but it's not standard convention. I'm sorry if you. So these are polynomials in sim tensor ZQT H lambda, and they are defined by two triangularity properties. So there are three properties. Any two define, any two imply third. And the first one is that H lambda Q minus 1 X is a span of monomials less or equal to lambda. This is dominance order. These are monomials. So then there is a similar thing where you use where you have transposed partitions, and then they are orthogonal for the Qt modified scalar product. Where so fg qt equals f of so now you have term in for q and t. Of course, it's the same as minus symmetric expression in t, but I wrote it for a reason. And there is also another normalization, right? And there is normalization because from the first, from these properties, it's not clear. There is a scalar freedom, but any two imply the third. So then normalization is that if you evaluate it at 1, you get 1, which is equivalent to, if you prefer the more standard, that this ordinary scalar product equals 1. Okay, so this is the modified Macdonald polynomials. It's not trivial to prove that they exist, and proof goes by reading, taking the Macdonald book and then modifying the polynomials according to the recipe of Garcia and others. So one remark. Let's set t equals 0. We get those polynomials from Hall-Littlewood. We had before. So I didn't tell you how to prove that the Hall-Littlewoods are images of the objects in that whole algebra story. And now you can see this definition of Macdonald polynomials, and you can simply set t equals 0 everywhere. And then you can check that those functions satisfy. So for instance, orthogonality is clear. Two different objects cannot be isomorphic, so they are orthogonal. Okay, and so, and then you can prove one of the other two triangularity properties. It's not that hard. So, right. So this is the problem, and this is about to get Macdonald, how to get Macdonald polynomials, and here is the answer. So. So you consider sigma algebraic curve, algebraic complete curve of genus G over Fq. And the idea is to count bundles. So we want to count bundles. With an important endomorphism. So before we were writing sum over some objects, 1 over the automorphisms, and then partial flux. So here is how we want to do it, how we translate this to, so we have this kind of sigma, and on the sigma we leave bundles with endomorphism. So these are pairs, E and theta, where theta is from E to E, nilpotent. And we want to get symmetric functions out of this. So the way to do it, what we can do, we can study observables by taking a point on the surface and evaluating our nilpotent operator in that point. So we also pick points z1 to zk on sigma, and we have this kind of evaluation maps. So evaluate theta at point z1, z2, and so on. Okay. And when we evaluate, we get a vector space with an nilpotent operator. So we get an object of we get a map to this whole algebra of this single loop quiver. So this is a picture. Now we have problems. That the problem is that there are too many bundles. If you don't, so again, we will be counting like 1 over the automorphisms, but if you do it on the nose, then we get an infinite, like a divergent answer, which doesn't make sense. So we need to truncate. To truncate the stack of bundles. And here is a, let's call it Ala Schiffman. He was computing volumes of this text using this truncation. So definition, a good truncation is a subcategory of the category of coherent sheaves of Koch sigma, such that if F is a subcategory tau, if F is in tau, then and G is inside F, then G is in tau. So sub-objects, if objects are good, then every sub-object is good. And second is that if short exact sequence then F and H is in tau, then G is also in tau. So closed under extensions, closed under sub-objects.
Anton, what do you mean by sub-objects? Like if I twist F by something negative, that's my twisted arbitrarily negative, that's good for you?
Yeah, these are very negative. In particular,
so like O of minus million is good for you because if it's in O or something like that.
Yeah, but O plus million is not. So example, but to see bundles are also good because a sub-bundle of a bundle is a bundle. It's more natural to
no, but you want this, I don't understand. You want this map of sheaves, you want to be a map of bundles, or it can be a map of sheaves without being a map of bundles? That's what I was asking. Like O of -1 inside of O is not a subbundle. It's a subsheaf.
It's a subsheaf. Yeah, it is. I want subsheafs.
Okay.
Right. So example, define tau. So f is in tau if and only if f has no subobjects G such that degree of G is positive. Okay, so f has no positive degree subobjects. Okay, in particular, f must be a vector bundle. Because any torsion sheaf has positive degree. So this is a notion of good truncation on the category. And then here is the, so when we count, we only count objects in the truncation, f theta such that f is in tau. We have weight by t to the minus a degree divided by the automorphisms. Okay, so this is what we will be counting. Right, so I mean, probably if you're confused, if you're used to count positive things, then you just use duality to get them to negative. But, okay, and now the theorem. So for each sigma and tau, there exists some functions omega, lambda, depending on qt. So lambda goes over all partitions such that the answer to the counting, so I have to, I don't know, the answer to the counting is sum over all partitions. Well, if you restrict the, let's say you restrict the rank, then it is omega lambda qt times Macdonald polynomials so I will explain. So each of them, the xi is a set of variables. And so this is is viewed as an element of Hall, tensor Hall, tensor Hall, tensor Hall. And I just rephrase it as a function in several sets of variables. Okay, so this is a statement.
This must somehow depend on the Frobenius eigenvalues of your curve, no?
They are sitting inside this omega.
And how do they sit? They sit as symmetric functions also as a...
They depend on tau. So there is, if sigma has genus higher than 0, then there is some freedom in choosing tau. There is one way to choose tau, like in the example I said. For that example, Schiffman computed this omega. It's not nice function, but has some expression. But in general, I think that it's interesting to search for different tau, try to compute it for different taus.
I guess what I was asking, it's also a symmetric function in the Frobenius eigenvalues somehow of a certain degree, or it's or some more complicated function, or it's...
Well, for that example, when tau is like I gave an example, yes, there are some explicit symmetric functions in the Frobenius eigenvalues.
Okay.
So in genus 0, so no, maybe first. So in fact, each term in the sum corresponds to, so this is pairs where theta is equivalent to n lambda in the generic point. So, and the idea of the proof is by, so there is this idea, is that E and theta are in tau, if and only if. So E is in tau, right? E is in tau, if and only if the kernel of theta is in tau. So given E theta, and this allows you to, if whenever you change, you do some local modifications of your bundle, preserving the kernel of theta, you're staying inside tau. So the idea is to sort of straighten out your theta in all points where it is where it kind of can jump. And you get this kind of product formula. So this goes to proof of the product formula for each lambda, for fixed lambda.
Anton, is your formula true for in some form for like nodal curves?
I don't know what is bundle over a nodal curve. I think it's a good. You're muted.
You're muted.
And so I think if you have a nodal curve, you can imagine you have all of your marked points on a separate component, and the all separate component talk to the mother component, and that's kind of the shape of your formula. There's some kind of mother thing of the, there's some genus, and then there's little peons on which the marked points sit.
Well, I guess when you glue curves, you just use the scalar product. You just have to identify the vector spaces, right? If you have 2 points and the vector bundle, you don't glue them together. Then you just have to identify the vector spaces so that the nilpotent operator is preserved, right?
Yeah.
And then it means that you get some kind of TQFT, right? You just need to use this whole scalar product to glue.
Yeah, I didn't mean to take away time from your talk, but I mean something to.
Okay, so genus 0 case is particularly simple, is much simpler. and then that omega. So there is only one sensible choice of tau. There's only one tau, because every bundle is a direct sum of line bundles. You just have to say which line bundles are in tau. And then you just say, okay, let's say all negative are in tau and all positive are not. So there is only one tau, and there is omega, and omega of qt is given by the product of cells 1 over q to the arm. Well, the usual. So these are arms and legs. Arms. And then somehow the proof that these are Macdonald polynomials, that this thing is exactly this formula, goes just by checking the properties and computing for the case of 2 marked points. By uniqueness of Macdonald plus 2 marked point case. Yeah, okay, that's the main statement. That's guess it's better if you ask questions and then I just try to answer and stop here. I mean, you'll stop, you ask questions.
Question: what kind of formula is it for generalizations? This lambda, this omega lambda.
It's so for z tau. The problem is that I think that tau is not the good one, not the right one. For instance, it's somehow not invariant under Serre duality, right? Something negative becomes something crazy. Sorry, so yeah, it's not a good thing. So I think you don't get good lambda, good omega. But it's some formula.
You mean you mean the particular tau was the one which has no subshifts of positive degree? That thing that you
Yes.
refer to.
Right. So it would be better that if there was some kind of better measure on the stack that somehow maybe should be invariant under Serre duality.
And okay, and if you cannot say what this function is, maybe you can explain how it is constructed or how its existence is proven in broad terms.
You mean that the formula for the omega? Again, you are muted.
You have to somehow either prove that it exists, or it's or give a formula for it, or there's a.
Well,
your theorem says there exists functions, and I was my question is, can you say a few things about them? How do we know they exist?
It depends. So you see, from this theorem, it just means that if you don't have any punctures, and you just compute the bundles with nilpotent endomorphisms. That will give you omega, right? One way of.
No, I think you need at least one puncture, right? To like you have one puncture, then yeah, it's otherwise you just get sum. To untangle the sum, you need at least one puncture, right?
No, but when I said that each term in the sum corresponds to sigma theta, where to e theta, where theta is n lambda in the generic point. So either you want to compute it for.
Okay, that's not what it's saying.
Yeah, I don't know what's easier here. Maybe it's easier to have one puncture. But I can tell, so Schiffman computes this sort of thing by brute force. You think, so you have a bundle and you have an important endomorphism. That endomorphism has certain decomposition. There are kernels, image of one into another. There is a way to describe completely an nilpotent object in an abelian category. I mean, object with nilpotent endomorphism in any abelian category. There's some combinatorial structure, and then it is reduced to counting certain flags of bundles. So, and that's how Schiffman computes this.
Okay, more questions?
Is this notion of good truncation related to stability in some way, or is it different?
You can say it like that. It's just restriction on the type of stables, right? So it means that all slopes are negative and non-positive. Object is here even only if all slopes are non-positive. Yeah, I didn't say that also that t equals 0 is, when you say t equals 0, then it means you restrict only to the degree 0 bundle, and then it will somehow, if everything is nicely, at least for genus 0, you automatically get the story of Hall-Littlewood polynomials, which maybe is nice. And in genus 0 case also you can have nice, you can have combinatorial formulas for this stuff, like counting bundles, means that every bundle is a sum of line bundles, so you're going over tuples of integers, and then you have to count how many polynomial nilpotent maps you have.
There's some, is there some like algebra acting by correspondences here somewhere? Is there some, or some kind of structure like that, or whole algebra structure, I guess, or?
I'm advocating for some kind of fusion whole algebra. So you have usual whole algebra on the finite category, on the category of this quiver with one loop, right? And then you have some correlation functions obtained by taking this, so this picture.
Yeah.
Right. So it's some kind of, it's like you have a
It's like a vertex. It's like a vertex whole algebra.
Yeah. And that's way. So I always used to think about Hilbert scheme. Right. Take Hilbert scheme. Then there are two things you can do. You can tensor bundles, or you have Nakajima operators, and you can see that there's like one like horizontal structure and vertical structure, and one of them will be the usual whole algebra structure, and another will be this correlations, give you the correlators. I mean, I mean, this formula here means you take some bundle which corresponds to omega on the Hilbert scheme, some, I don't know, some crazy bundle omega, tensor with purchases, and take the index on the Hilb. And
I think on some number of copies of Hilbert scheme, not on.
no, on the same, sorry?
I thought you get like a bunch of different variables, so you should go to, shouldn't you go to a bunch of,
So lambdas are fixed points on the Hilbert scheme. And the thing you are taking is this fibers of the Purchase bundles of the Macdonald polynomials. And then everything, all the complexity is somehow hidden in this bundle. Which depends on the curve and on tau. Right? I'm summing over single partition, not over tuples of partition or anything more complicated. Just so
yeah, I understand.
Mm-hmm.
If I start with Higgs bundles on a surface instead of a curve, is there anything that could be said?
Maybe what you mean is to consider a curve inside the surface. And I mean, replace Higgs bundles by some coherent shapes on the surface.
Yeah.
That would be analog because.
But there's aren't even Higgs bundles here, right? You don't go to, you go just to shift itself, not shift tensor differentials on the curve.
Yeah. Well, that's what I'm. So there is, using Serre duality, you can relate two counts. This is some funny thing. Like if you have a bundle, then dimension of home equals the Euler characteristic plus dimension of h of x. And this equals to the dimension of home from E to E tensor omega 1. And this is fixed. For given fixed degree and rank. So on the level of counting, there is no difference between counting Higgs bundles and counting endomorphisms. And well, this is what is used to prove some results about Poincare polynomials of the moduli spaces of Higgs bundles. So it's maybe, I don't know how to realize this Serre duality using some explicit correspondence or something like Fourier transform thing.
So I guess what Noah was asking is that this kind of Higgs bundles, and they make sense for, in fact, you know, in arbitrary dimensions, you can do try bundles on a surface, see what happens there, but
So you obtain formulas for Higgs bundles, but they are they can be deduced from that formulas but you have to pass from nilpotent, from counting nilpotent endomorphisms to all endomorphisms, and then via this formula to Higgs bundles. But if
Oh,
it's better, for instance, take a little bit positive, a little bit more positive than Higgs, then there is a better. So there are some nice formulas for this.
all right. Maybe we should thank Anton for a wonderful talk, and then we meet again next week. So I don't know. Thank you, Anton. Thanks so much.
Thanks.